Assalamualaikum, and we meet again. So this is for DC power supply subtopic. Okay, so actually for DC power supply that actually based on power electronics, it has a special name that we call switch mode DC power supply or SMPS. So compared to the linear power supply, linear power DC power supply, it has several advantages. For example, more efficient, small in size and weight. However, the design is very complicated, and also it has some harmonics and electromagnetic interference. So actually, the advantage is actually more efficient and small in size and weight only. Okay, but some of the difficulty in the switch modes and SMPS is actually it's a complicated design, and also it will involve the harmonic and electromagnetic interference because it involves a switching. So when you have a switching, so it will create some interference to other system. Okay, so this is actually the general or typical block diagram of what called the SMPS. So for example, we have a DC power supply here, AC power supply. So we have the what called electromagnetic interference filter. So this filter is actually to cut interference that come from this conversion here to go back to the AC supply. Okay, so the EMF filter will actually cut that noise. Okay, and then from AC, so this is also AC, so we go into rectifier and filter, so meaning that the output of the rectifier will be a DC, and this one is what we call unregulated. Unregulated DC. Unregulated DC meaning that this is actually not a process DC, because we need to regulate this according to our load. Okay, according to our load. Maybe our load requires maybe 10 volt. So this unregulated, maybe output of the filter may be around 20 volts. So we need to regulate it to step down it into a 10 volt. Okay, so this is actually where the SMPS, okay, sorry, the DC-DC conversion and isolation here is done. So actually it will be processed step up or step down, and we have this what I call the feedback. So this is PWM controller will give you the duty cycle. Okay, what is the required duty cycle to match this voltage of the load. So as you can see here, this transformer is not a linear transformer. This one we call high frequency transformer. So the function of the high frequency transformer is actually similar to the linear frequency transformer, but it has smaller size and very compact, and also a very lightweight compared to the linear transformer. And this high frequency transformer is actually not appropriate to be used at line frequency, for example 50 or 60 hertz. So this transformer is purposely designed for high switching frequency. Okay, so type of DC-DC converter that is used is in SMPS. We can categorize under actually four. The main one is the flyback converter. So flyback converter is used in our Apple Mac charger. Okay, this is the most popular one. And then we have the half bridge converter, full bridge converter, and also a forward. And then we have another one what we call push pull. Okay, push pull converter. But this one will not be in our syllabus. So all 4 or 5 of these converters is actually an isolated converter. So compared to buck converter, boost converter, and buck boost converter, so these 4 converters are isolated using the high switching frequency, meaning that the advantage of these converters compared to the original converters, the buck, boost, and so on, is actually we have the isolation. Okay, so meaning that it has a safety features. So this is actually why we are using isolated DC-DC converter is actually for electrical isolations. Okay. So this is the transformer. So as I said before, it provides two functions, which is electrical isolation and to step out, to step down the voltage and also the current. Okay, so still the equations involved is still the same, which is V1 over V2 is equal to N1 N over 2, and for the current is actually same. So we have I1 over I2 is equal to N2 over N1. Okay, and this is actually the electrical schematic. Okay, so for the high frequency transformer. Okay, and this is the model. So this is the model that we will use in our power electronics analysis. So we have the primary and then the secondary, and then we have what we call LM. So LM we call is actually a magnetizing inductance. Okay, LM. So there's a current here, ILM, that we will actually discuss further. Okay, and then as you can see, we have a dot here. So if you recall back this dot, so if the current is going, if the current is going into the dot, at the secondary, the current must go out from the dot. Okay, that is the law. So if your current in the primary is going into the dot, so the secondary, the current must go out from the dot. So based on this slide, so the value of LM is very important in this isolated DC-DC converter because most of the analysis will be based on LM. Okay. So this is the flyback converter. So it's a very simple circuit. So we have a single DC source, a switch. This switch must be a transistor, fully controlled. Okay, transistor, and then we have what we call high frequency transformer. Okay, a diode, a capacitor, filter, and your load. Okay, so actually the flyback converter is actually a buck boost converter. Okay, it's a flyback boost converter. So for further analysis, so we switch to the whiteboard. Okay, so this is the circuit of the flyback. Okay, so we have here the DC source. We have the transistor model here. We have primary, secondary, and also LM. Okay, the diode, capacitor, the voltage. So we have a switch here. So meaning that to analyze this circuit, what we should do is to analyze in two conditions. The first one is when the switch is turned on, and the second one when the switch is turned on. So we will start with the switch on. So what happened when the switch is on? So when the switch is on, so what happened? Okay, so there will be a current source flows. So and then it will be divided into two currents. So this one is ILM, and this one is your I primary. So this current will go into the dot. So meaning that at the secondary, current will go out from the dot. So this is your I2. So this one IC, and this one is your I out. So this should be all actually time dependent. Okay, time dependent. So as you can see, the current is going this way. So meaning that this diode will be actually reverse bias. Okay, so what is mean that when it is reverse bias, so this one is V1 and this is a polarity for V2. So when it's reverse bias, meaning that I2 is 0. So when I2 is 0, okay, so the I2 is 0 and the circuit V out and V2 is disconnected. So meaning that your V2 is 0. Okay, so I2 0 and V2 is also 0. What is V1? So V1 is actually, we can, if you refer back to this ratio, V1 over V2 is equal to N1 over N2. So V1 is actually N1 over N2 multiplied with V2. So right now V2 is 0, meaning that if this one is 0, so meaning that V1 is also 0. So when V1 is 0, okay, V1 is 0, and then we look at I1. I1 is referring to the equation is actually N2 over N1 multiplied with I2. Okay, so if I2 is 0, meaning that I1 is also 0. So meaning that there is no current flow inside the primary side. Okay, so all this circuit here is not functioning. The only circuit that functioning during the switch on is actually this two. So the current will actually looping inside the magnetizing inductance. Okay, so the KVL at that loop can be written as a negative VDC plus VLM, and then is equal to 0. Okay, so VL magnetized inductance is positive VDC. Okay, and then we have already know that VLM is delta ILM over dt, so positive VDC, and this one can actually as a D on, so this one VDC over L, and we know that delta T on is actually a dt. So finally, the last equation, ILM on is equal to VDC over, also this is LM, okay, magnetized inductance multiplied with dt. So this is actually the equation that we got from the analysis during switch on. Okay, so now we continue to analyze the circuit when the switch is open, okay, or switch is off. This switch current, the switch is off. So when the switch is off, what happened to the I source? This I source IS will definitely become 0 because there is no closed circuit here. So IS is 0 right now. So meaning that the DC source is disconnected totally from the circuit. So the inductor here, magnetizing inductor, will become the energy source. So it will actually discharge its energy. Okay, it will discharge the energy. Okay, so right now this is your I1. Okay, so your I1 right now is like this. So it's actually going out from the dot. So meaning that when it is going out from the primary, so the secondary meaning that it is going into the dot. So this is I2. Okay, so this is I2, and the direction of the current is actually in the same direction of the diode. So meaning that this diode will be forward bias and can represent as a short circuit. Okay, so this is the I diode. So it will be ICT, and this is your I out. Okay, so this is actually the circuit when the switch is turned off, when the switch is off. So what we can see here, the V2 and V out. Okay, V2 and V out is in the reverse polarity. So we can say that, or if you use a KVL around this loop, okay, so V2 is actually a negative V out. Okay, and for V1, we can obtain V1 by using the transformer equation. So N1 over N2 multiply with V2. So V1 right now is N1, N2, because V2 is negative, so negative V out. Okay, so negative V out. And we know that this V1 is actually parallel with the inductor, magnetized inductor. So this is VLM. Okay, so we can say that for the VLM, which is LM DILM dt is equal to negative N1 over N2 V out. And this one is actually delta ILM over delta T off, which is negative N1 and 2 V out. Okay, and we know that delta T off is actually a 1 minus dt. So delta IL during off, we can LM everything off is negative N1 N2 V out multiply with 1 minus dt. So we have this one delta IL on, okay, minus delta ILM during off should be equal to 0 in steady state. Okay, so we substitute the delta IN, so this is actually BDC over L and dt minus N1 N2 without 1 minus dt this one is over L M. Okay, so this one is actually over LM. This is actually over LM. Okay, so it's equal to 0. We will actually got the equation, which is the flyback converter, which is V out is equal to D over 1 minus D VDC. Okay, so this is the equation of the flyback converter. So for D that is over than 0.5, so it become boost. If D is less than 0.5, become buck, and D is 0.5 is actually just is actually equal to its own. Okay, I hope you understand on the analysis, KVL analysis on the flyback. So we will continue on the magnetizing inductor current in analysis after this.